right, this is one of the forces video. The first thing that we need to talk about is the difference between speed versus velocity. So speed is the measure of how fast an object is going. Velocity is a measure of how fast an object is going in a given direction. Speed is a scalar quantity. Velocity is a vector quantity. In fact, speed is part of velocity because velocity is speed plus direction. So acceleration, right? Most people use this term just to mean speed up. However, in physics, it has a very specific definition. Acceleration is how fast velocity changes. Acceleration is a vector quantity. So that means it has a direction. So a net force must be applied in order for an object to accelerate. And there are three ways to accelerate: speed up, slow down, and turn. So could you accelerate without changing speed? So think about the controls in a car. What controls in a car cause a change in speed? Well, the gas pedal and brake change the speed of a car. Now, what control or controls in a car will always cause a change in velocity, but not necessarily a change in speed? So the steering wheel will cause a change in the velocity without necessarily changing the speed because the steering wheel causes a change in direction. A car could take a turn going 30 miles per hour all while just changing the direction, and that speedometer would read 30 miles per hour the whole time, right? But that car would be changing velocity, but not speed. So now what controller controls in the car cause acceleration? So all three of them, the gas pedal, the brake pedal, and the steering wheel all cause an acceleration because the car would either be speeding up, slowing down, or turning. So now acceleration. Notice that I did not say how much velocity changes, but rather how fast velocity changes. There is going to be a time interval involved. So if you think back to car commercials, you might hear this, it goes from 0 to 60 in so many seconds. That is explaining acceleration. So how fast velocity changes means that we compare delta V to delta T. So change in velocity to change in time. So that triangle is delta, and that means changing. Right? So, and that arrow over some of those variables means that those are vector quantities. The direction needs to be taken into account. So acceleration, in order to calculate that, you need three things. You need the starting velocity, which is the v. So that's at time 0, at the beginning of that time interval. How fast is that object traveling? The final velocity, the ending, that's the ending velocity at the end of that time interval, and the time interval over which this change took place. Now, the unit for acceleration is is a unit of velocity per unit time, or meters per second squared. Now, a second squared, that's not a unit of time. It's not like a special unit of time. What that is, what that means is that it's technically meters per second per second. How much faster is that object traveling every second? And that is what an acceleration is. So if we get some practice problems, so suppose a driver increases her velocity from 5 meters per second to 12 meters per second in a time of half a second. So if we look at that final velocity, think about telling a story. At the end of the velocity, that driver is going 12 meters per second. At the initial velocity, at the beginning of this time interval, that driver was going 5 meters per second. Now the time interval is 5 seconds. I plug everything in and I get 14 meters per second squared. Now let's look at this another problem though. So now suppose the driver decreases her velocity from 12 meters per second to 5 meters per second in a time of half a second. So now the final velocity is less than that initial velocity. So when you plug everything into the equation, you're going to get a negative value, negative 14 meters per second squared. Now, what is negative acceleration though? So recall that acceleration is a vector quantity and it has a direction, which means it has a direction. So negative acceleration doesn't necessarily mean an object is slowing down. If an object is speeding up, the acceleration will be in the same direction as the velocity. If an object is slowing down, the acceleration will be in the opposite direction of the velocity. And if an object is at rest or at a constant velocity, the acceleration will be 0. So if we look down here, the acceleration, notice that it's moving to the positive direction, and this car is speeding up. So the acceleration will be in the same direction, in the positive direction. Now, this car is moving in the positive direction, but now the acceleration, now it's slowing down, so the acceleration will be in the negative direction. Well, these next two examples, the velocity is going in the negative direction. In that first one, the car is speeding up, so the acceleration will be in the same direction. So now I have a negative acceleration, but it's speeding up. And in that last one, the car is slowing down, but the velocity is in the negative direction, so the acceleration will be in the opposite direction, or that positive direction. So this activity, the name that motion activity, helps identify like different types of motion, like different directions, the velocity, the acceleration, even the speed. Just looking at a car that's traveling, and it shows little dots to mark that motion. So now let's talk about force. So a force is a push or a pull in a direction. A force is a vector quantity, which means it has both magnitude and direction. And the unit for force is the Newton. Now we can represent a force by a line with an arrow to indicate the magnitude and direction of that force. So the six types of forces that most books and places talk about are that sometimes these forces are split up into different ones. Sometimes they add another one. But these are the main ones that cover most of the forces in everyday life. So there is gravity or weight. It's called weight. There is the normal force. That's that perpendicular support force. So if you look over to the right on those graphics, you can see that there's a box on a table. Well, gravity's pulling down on that box, but there's a force preventing it from falling down to the center of the earth. That's the normal force. That's the perpendicular force. Then there's the applied force from a person or object onto another person or object that attempts to change the motion of the object. There's a force of friction, which opposes sliding motion. There's drag, air resistance, or also fluid resistance that opposes motion through a fluid. And there is tension from a rope, string, or a spring. Now, forces can add to each other. So think about it this way. If somebody's pushing a car, if one person is pushing in one direction, another person is pushing in the opposite direction, those forces will not help each other out. But if they're pushing in the same direction, those forces will help each other. This is called net force. Now, net force is the sum of all forces acting on an object. So if we have two people, one person is pushing on this box and then another person's pulling, but their forces are going in the same direction, those forces help each other out. You just add all the forces acting on that box together, and that will be the net force. So net force, it doesn't necessarily mean that that force will increase. So if I've got two, yeah, if the forces are going in the same direction, that net force will have a larger magnitude. But if forces are going in the opposite directions, well, they're not going to help each other out. And then you can do like forces at different angles. All right, so now let's talk about balanced versus unbalanced force. So balanced forces, all the forces cancel out. The net force is 0 newtons. The object is at rest or at a constant velocity in a straight line. Now, unbalanced forces, all the forces do not cancel out. The net force is not 0 newtons, and the object will be accelerating. So think about it this way. Let's just say there's an astronaut in space, right? So we're far enough away from anything that we can sort of negate any gravitational pull, right? So we can say that the net force acting on this astronaut is 0 newtons. Now let's just say another astronaut is passing by, traveling at a constant velocity. Well, the net force is still going to be 0 newtons on this astronaut. There's no forces acting on it. They're just acting on this astronaut. Now, the reason why we say that rest and constant velocity are the same thing is because on both of these scenarios, the net force is 0 newtons. In fact, if you were to ask these astronauts when they get back, like which one of those astronauts was moving, both of them would say the other astronaut was moving towards them because from their perspective, they wouldn't feel that motion. They would just see the other astronaut coming towards them and passing by. They wouldn't feel anything different. Now, if a spaceship traveled by that turned on its thrusters, right, then there is an applied force. It's going to be moving in a direction because there is a net force acting on it. So that must mean that the rocket will be accelerating. So this rocket is accelerating. If these astronauts are on there, they will feel that motion. Think about it this way: if you're at rest, if you're at a stoplight in a car, you're the passenger, and you're drinking some water, you're going to feel natural. But then if you're drinking some water and somebody slams on the accelerator, slams on that gas pedal, you're going to spill it all over yourself, and you're going to feel that acceleration. You're going to feel that motion. Now, later, if you're driving on a highway and you're going at a constant speed in a straight line, so you're not accelerating, well, you could drink that cup of water normal. You wouldn't feel that motion. You'd feel normal. You could drink that water. You could take a nap. You'd feel normal because you're not accelerating. Because, remember, in physics terms, there is no difference between being at rest and moving at a constant velocity. Acceleration is only the real motion. That's the one that people feel. All right, so kicking a football. So what forces are being applied to this football as it's being kicked? Well, if I'm looking at this one, I know gravity's pulling down. And I know that there's going to be an applied force. There's going to be applied force acting on this football. So is the object accelerating at a constant velocity or rest? So let's look at everything that we know. So we know that gravity is pulling on it, and we know that there's going to be a large applied force. So that's really it. There might be some small, drags, maybe some air resistance, but yeah, overall, these are the two main forces that are acting on it. And this would be the net force acting on that. So if I look at this, I know the object is going to be accelerating, right? I know it's going to be accelerating because, well, it started at rest when that player was holding the ball, and now it's accelerating. It's increasing its speed. And I know the net force will be equal or not equal to zero. I know that there is a net force acting on this because this object is accelerating, and all the forces are going to be unbalanced. There is that unbalanced net force that is causing that acceleration. So let's look at an example, the deadlift. So as the barbell is resting on the ground, the net force is going to be zero. All the forces cancel out and the forces are balanced. Now, as he lifts the barbell off the ground and is moving up at a constant velocity, so yes, he did need to make a little acceleration to get it moving, right? So start at rest, increase it. But after that, he can lift it at a constant velocity. Well, the net force is going to be equal to zero because, well, he's just canceling out that weight as he's lifting it up. And the forces are going to be balanced. Now, as he lets go of the barbell and is accelerating down, the net force is going to not be equal to zero. There's an unbalanced force accelerating that barbell. All right, so, how can we represent forces? So, here is the free body diagram. Forces acting on an object can be represented by a free body diagram. So, just draw a dot representing the center of mass of an object, draw arrows pointing away representing the forces, and then label the forces. So, that's what a free body diagram looks like over there. It's all the forces labeled on an object. So, let's get some examples. So, let's play this clip of a horse is slowing down by skidding on the dirt. Is this object accelerating, constant velocity at rest? Will the net force be equal to zero or not zero, and all the forces balanced or unbalanced? So I know that this horse is going to be accelerating. Now, that might not make any sense. You may be saying, well, the horse is slowing down. How can it be accelerating? Remember, there are three ways to accelerate. You can speed up, you can slow down, and you can turn. So yes, this object is accelerating, which means the net force will be not zero because the forces are unbalanced. There's an unbalanced force causing that net force, causing it to accelerate, causing it to slow down. So if we look at this example, I know the forces that are acting on this horse are going to be gravity, the normal force, frictional force, and that's it, right? Now it may be moving in the right direction, but remember the acceleration is caused by that net force, so it's accelerating in the left direction because it's slowing down. This would be the free body diagram associated with this object. So let's look as the sun orbits around the sun at a constant speed. Well, I know that the earth is going to be accelerating because it's turning, even though it's traveling at a constant speed. And yes, if you look this up, it does travel at different speeds, but relatively it's about the same. So, but it is accelerating because it is turning. So I know the net force is not going to be equal to zero, and the forces are unbalanced. There's that net force causing that acceleration. So if I'm looking at the forces that are applied to this, to the Earth, what's going to be gravity? Gravity's pulling down, and that's really it, right? The net force, technically, the Earth is accelerating down towards the sun. It's just falling over the curvature of the sun. That's the free body diagram for Earth. Now let's look at a bowling ball. Now the bowling ball travels down an alley at a constant speed in a straight line. The object's not accelerating because constant speed, straight line, so not speeding up, slowing down, or turning. The net force is going to be zero. Well, there's all the forces balance out. They cancel out. The net force is zero. There's no acceleration. It's traveling at a constant velocity. So let's look at the forces being applied to it. So I know I have gravity and I know I have normal force. Now, yes, there would be a small, very, very small drag, but at these speeds, we can just negate those small drag forces. And, well, since it's rolling and they do grease the floor, we can also negate that small frictional force. So yeah, there would be small forces slowing this down, but overall, those are small enough that we can negate them. And we can just say the net force overall is going to be 0 newtons, right? So this is what the free body diagram will look like. Now let's look at another example. Now as a bowling ball travels down the alley at a constant speed and is slowly curving towards the pin, well, I know the object is accelerating. Even though it's traveling at a constant speed, it is turning. So there is a net force. So the net force is not going to be zero, and the forces are going to be unbalanced. So let's look at the forces that are being applied here. So I'm going to have that force of gravity, and I'm going to have that normal support force, that the perpendicular support force. Now that force that is causing it to curve in, Well, last time when it was traveling in a straight line, well, we just sort of negated that frictional force. But if this person gets it spinning to the side fast enough, there will be that small frictional force that will cause a net force to turn this ball. So this free body diagram is a little complicated because, well, the bowling ball is traveling like into the screen, but the net force is to the left, accelerating it, causing it to turn. So this brings us to a couple of simulations that might help out: the balance versus unbalanced force activity and the match the free body diagram activity that would help out. So now let's talk about the difference between mass versus weight. Now, mass is the measure of the amount of matter or stuff in an object. It is measured in kilograms. It does not depend on location. It is closely related to inertia. It cannot be measured directly. It only has a magnitude, which makes it a scalar quantity. Now, weight is the measure of the force of gravity on an object. It's measured in newtons. It can change with location. It's closely related to gravity. It can be measured directly with the scale, and it is a vector quantity. It does have a direction. So, what does it mean that it changes? That it changes based on location. So think about it this way: mass, well, does not change on location. Mass is just a matter amount of stuff that makes up a person. Well, if I have a mass, I'm made of stuff. Now, if I went to the moon, that wouldn't change the amount of stuff that I'm made out of, but it would change the gravitational pull on me. It also changes based on your location on Earth. So the farther you are away from the center of the Earth, the less the gravity is. So the lighter that you weigh. So let's talk about actual weight versus apparent weight. Now, there is a difference between gravitational pull on you and how heavy you feel. So think about like riding in a roller coaster, on an elevator, or even like on a country road that goes up and down. Like you can feel lighter. Actual weight is the measure of the force of gravity on an object, while apparent weight is how heavy a person feels and is dependent on the normal force. Which brings us to another question: how does being in water affect a person's weight? So does being in water affect the gravitational pull? So no, when you're in water, you still have a gravitational pull on you, but you don't have that normal force. That normal force is what causes you to feel that weight, right? So, but there is a buoyancy force that is holding you up, and you don't necessarily feel that buoyancy force. So you have a net force of zero, but you feel weightless when you're in water. You don't feel that weight, right? Now think about the like whales that get beached, that wash up on the beach. Well, there's a rush to get them into the water because when they're in water, they don't really feel their weight. Yes, gravity is still pulling on them. They have a large, like actual weight, but they don't like they don't have a large apparent weight. They don't really feel that gravitational pull. Now, when they're on there, then they're on the beach. They have a normal force acting on them, and their weight actually starts to crush them. So that gravitational pull starts to crush them. So that's why. That's the difference. That's why you can feel lighter, heavier in an elevator or a roller coaster. It's that normal force that makes you feel that weight. All right. So now, in order to calculate acceleration, or sorry, to calculate weight, you need to know the acceleration of all objects on that planetary body. Now, it does vary where depending on where you are on Earth, right? So usually about negative 9.807 meters per second squared, but to simplify it, we're just going to use negative 10 meters per second squared. So that's the acceleration of all objects on this planet. Now, notice that, well, the force of gravity will be negative because it's pointing down, right? Weight is negative. It's just always implied. It's always implied that it's just implied that your weight. You're given a magnet. It's always going down. If you say, "Hey, how much do you weigh?" Nobody's going to say I weigh negative 130 pounds, right? It's just implied that it's going down. But when you're calculating it, you need to realize that it is going down. Now, notice it's a very simple equation, right? The force of gravity, that weight, is just the mass times the acceleration of all objects on that planet. All right, so let's just go over some problems. So an object has a mass of 12 kilograms. What is the weight of the object on that Earth? So all I do is I plug into that equation, and I just multiply the mass times the acceleration, and I'm going to get, well, negative 120 newtons. Now, if you know the weight and you're trying to calculate the mass, well, you just plug it in that equation again, and now you take the weight divided by the acceleration, and you're going to get the mass. It'll be 9 kilograms. Notice to keep track of those significant figures. Now, this activity was your weight on other planets. So in this one, you take a 50 kilogram person that goes to the other planets, and you need to to calculate it gives you their weight. Now, it'll give you the weight and positive. It will just give you the magnitude. However, remember, it's negative because it's going in the downward direction. So this is what, notice that the weights are given to you in a positive number, but you do have to add that negative because when you're calculating the acceleration of all objects on that planet, you do need to know that it's negative, right? So you just take the weight that divided by the mass, and you're going to get the acceleration. Now, these questions will help out. So this first question, well, this is about mass. Just tell me everything about mass. What's the unit? Does it depend on location? Can it be measured directly? Is it a scalar quantity, vector quantity? And just explain these answers a little bit. Same thing with weight. Now, this last one is like the crux of everything, right? Of all everything with weight and mass, right? Why does weight of an object person change on other planets? The mass remains the same. And how do mass and weight relate to each other? And I know they relate to each other because there's an equation that tells me that they do. All right. And as final thoughts, remember there is too much unknown in the universe to take a break from learning. Get out there and question everything.